All right, so getting started a little late. Sorry about that, but so we really only have a few sections left, all from chapter 10. And I just before I get into chapter 10, I just want to make a few remarks about the test from yesterday and just kind of some general things and where we're going for the next week. We only really have a week left. The final is a week from tonight. So quizzes. I had the deadline for the quiz that was due tonight. I originally had it for 5 p.m. I only got half of them turned in. So I'm hoping people forgot about it, and that's why I have so few, but I have extended the deadline for that quiz tonight to midnight. So you have till midnight tonight on that. I'm going to post another one today. I'll go ahead and make that other one due tomorrow night as well. Just so you're not really stacking everything up that much. But yeah, if you're not aware or if it's slipped your mind, yeah, the test being due at 5 has been pretty consistent all summer long. So keep on those, keep in mind of that. There's only going to be one more homework assignment left. I posted that today. The deadline is actually going to be for that the day after our last class meeting. So it's going to be the day after the final. Obviously, it would be better if you all looked at it and got as much of it done as you can before the final. It's definitely going to be good practice. What else? I've started grading the test. I have not finished them. My plan is to get them done either tonight after class or early tomorrow morning. But so I'll have those in the grade book as soon as I can. So it might not seem like it because we only have really 7 more days left of class, but there's a lot of class left. So wherever your grade is right now, I'm not sure this for good or for bad, whatever your grade is sitting at right now is definitely definitely not final. There's a lot left. A couple things I should let you know about though. I don't know if there's a way in Canvas for me to drop your lowest quiz and your lowest homework, as we go, but I haven't done that. So the grade you have right now is at least as high as what you see. Keep in mind, there's, I have not put the second midterm test in there, but that's going to be over 20% of your grade, and the finals were 30% of your grade. So yeah, in a very real way, you're only half of your grade is kind of locked in right now. So having said that, you're going to see test grades. I would like to commit to tonight, but might have to be tomorrow morning. But those test grades are going to be in very soon, regardless. And if you have any concerns or questions about, your standing, your grade, or what that means for the near-term future for this class, please reach out and let me know. I'm definitely willing to have a candid conversation with anybody if you're worried. If you have any concerns, I don't want anyone to be surprised at the end of this. So yeah, if you have any doubts or any concerns, please let me know. And I know there's a lot of different degree paths in here, a lot of different majors. But just to let you know, I'm guessing for most of you, if you're in Calc 2, you're probably needing Calc 3 as well. And you're pretty much everything we've done this summer, you're going to see again. I mean, there are a lot of different ways you can get a look at differentiation integration, and when you go into calculus and differential equations, they're going to be there too. Specifically chapter 11, which is all sequences and series and all those tests, and chapter 10, what we're about to get into. So the first 2 sections in chapter 10 are these parametric equations, which you may not have heard of or seen before, and the last 2 sections are polar coordinates. these things are going to be, directly applicable immediately in Calc 3. So it would really, really benefit you to carry a good understanding of these things into Calc 3, which, from talking to a few of you, I know at least a couple of you are doing Calc 3 in a couple of weeks. So yeah, if you definitely don't want to start behind. So yeah, stay up to date on this. And for those of you who are going beyond calculus into things like 300 and 371, series and sequences, they only get more prominent. They're used for so many things in so many math disciplines. So I know the test is behind us, but if you have any questions or if you want to polish something up, short term, you're going to have to worry about a final. They're definitely going to be back. But longer term, this stuff we still have yet to do, and the stuff we have recently done is going to be around in a very real way for as long as you deal with math, and really in, most of the like engineering and science majors as well. So let's go ahead and get started, unless anybody has any questions, wants to talk about anything. All right, so chapter 10 is all about, like I said, parametric equations and polar coordinates. So basically almost everything, if not absolutely everything we've done in terms of, algebra, pre-calculus, all the way up to where we are now, has been Cartesian. So you look at a Cartesian graph, it's a rectangular grid. You have x-axis, y-axis. Parametric equations, we're still going to be looking at things on an x and y axis, but we're going to be adding another dimension, or kind of an intermediate dimension to that. So let's go ahead and get started. So quick question here. This curve I'm showing you, does this represent a function? What do you think?
I don't think it does.
Okay. And why is that? What's the thing you typically look at? I mean, I'm guessing it's probably on the front of most of your minds. What's the thing we typically look at to figure out if a graph I'm looking at is a function?
Oh my god. Is it dy by dx that we're looking for?
Well, if you can find a derivative, it definitely is a function. But we don't even really need to get into calculus to talk about whether something is a function.
This might be a function, right?
It might be.
It has to be a function.
It doesn't have to be. So what if I graphed something like this for you? Is that a function?
Of course, that's a parameter.
Okay. Why is this one I just drew, why is that one clearly a function while this other one we have some doubts about?
The second one's more uniform.
Or uniform? Okay. What if I did this? Is that a function?
It's not uniform throughout, right?
What do you mean when you say uniform?
I mean, it's like so for if you're dividing this graph, that the smiley face graph into half, you're gonna get that, that it's decreasing, like, I mean, you don't see that variance is there, like it's not like, it's just changing erratically, like that dy by dx at each point is like it's same. Whereas in the second one, it's like you have this it's so violent, and it's like there, here, there, like that.
Okay.
That's more. There's more variances or something, I guess.
Okay. So what I think you might be thinking about is is whether something is differentiable, but that's different from asking whether something's a function. So I'm going to go ahead and make a bet that most of you are thinking about something like this in your head. Just because typically, I mean, I feel like typically what I think about when you see it, when you're looking at a graph trying to figure out if it's a function, you're thinking of the vertical line test. So clearly, this curve I'm drawing that I copy and pasted here on the left, clearly this thing fails the vertical line test many, many places. And I think we're typically used to thinking of that as, all right, vertical line test fails. This thing is not a function. And that very well may be the case, but let's think about what a function is. So what is a function? So I'll remind you all of the most basic definition here. And the vertical line test, I mean, there's a reason that is a good thing to try, but it's not really specific enough. But basically, a function is a relation, and even this is still simplified a bit, but that's okay for where we're going, where every input is mapped to, at most, one output.
Professor.
Yeah, why don't we do that?
You're taking the vertical. I thought about that, but then I was thinking about it like with respect to the y-axis, but then you wouldn't really. Okay, yeah, even then you would have.
Yeah. So, and really, I left this question vague on purpose. You know, if I were to ask you for this one here, is y a function of x, which is usually what we're trying to figure out, which is exactly why the vertical line test, it does what it does. So if I was asking you, is y a function of x? Pretty clearly no, because let's just pick one, whatever this x value is. Clearly that x value has multiple y values that it maps to. So that is not a function. You know, whereas this thing, you know, it doesn't matter where I draw a vertical line, y is a function of x. And I might have messed up on this bottom one, but I tried to make something that, you know, looks strange and badly behaved, but really for every x value, I can just get a single y value. So if I was asking that, and which typically when you know, calculus students are asked, is this a function? That's typically what you're being asked, and that's typically what you try to answer. Which, even though I didn't hear it, I'm fairly confident that on a lot of people's minds was that phrase vertical line test. So let's look at this picture again. What if instead of, you know, thinking about, is y a function of x? Let's ask this other question. Is every generic point xy a function of, you know, this ordered pair of functions f of t, g of t? So you probably haven't seen anything like this yet, but that's okay. That's what we're going to be spending tonight working on, is this idea of this parameter t. Basically what I have here is I have some function f, which maps values of t to values of x, and I have some other function g, which maps values of t to values of y. And this, the answer is yes. Because every value of t gives me a unique xy pair. So all these points on this curve, they all come from a different value of t there is no value of t that's going to give me more than 1 point. And here's the reason that that's definitely not going to be as obvious as, you know, the classic question is why a function of x. When you're looking at this graph, all right, so really what I have here, I have right here's t. It goes into some function, and what comes out is points, ordered pairs. So that's a function, but what are we graphing here? Or maybe I should ask it this way, what am I not graphing on these axes? Could I ask you what the values of x and y are for that point right there? Or could you at least approximate it?
1,2.
Yeah, so I mean, you can, all right, let's go with that. Maybe it's 1, 2. Clearly, x and y are both positive. It looks like y is about twice as much as x. It sounds good. What does t equal there? And you have no hope of answering that because we don't graph t. So even though t governs these curves, it's kind of happening behind the scenes. You're not graphing t. We don't typically label these curves with all of these points with their corresponding t values. But really, you know, t is the thing that's, you know, making this whole thing work. So that's kind of in generalities. So let's look at one specifically. So I want to sketch and identify this curve here. And we're going to look at this interval. I want t to be inside this closed interval from -2 to 4. So first thing I'm going to do is this. I'm just going to build a list of points. And this is probably the thing that you've done every time you've tried to graph something by hand, just to make a table of values and gather a bunch of points, then plot. So we're going to basically do the same thing here with one little wrinkle. So go ahead. I'm giving you some t values. You have these recipes here, these functions. Basically, I'll make these more these are functions. Y is a function of, or sorry, yeah, y is a function of t, x is another function of t. So go ahead and start shouting out some numbers at me. When I plug these t values into these expressions for x and y, what values do I get? Or if you prefer, go ahead and throw some stuff at me in chat.
Eight and -1
For which value of t was that?
for -2.
-1, I believe.
And 3 and 0 for -1.
Okay. All right, who else has some?
0 and 1.
0, 1 for the next line. Go ahead and work from the other end. If you see any errors there, let me know. I think that's okay. So from there, I can go ahead and start graphing. And now that I have this table, I have a pretty good idea about, how to set up my graph. It looks like it's mostly in quadrant 1. So -1 to 8, and then I need -1 to 5. So as I plot these points, remember that everything is governed by t. So I'll just start plotting the points. So the first one is 8, -1, 3, 0, 0, 1, -1, 2, 3, and 8, 5. So I have all these x values, but like I said before, the way this curve is plotted has everything to do with t. So that means I can't connect these points in any order I choose. I really have to respect the order of t here. So t is -2 started here. And I'm going to just graph them smoothly like that. So what kind of curve am I looking at here? I like this sketch, but what kind of curve is this?
Parabola.
That's a parabola. So let me ask my generic question again. Is this a function?
Yes and no.
Yes and no. When you say yes, how do you mean?
If it's so good with respect to t, yes, it is.
Okay. CIS is a function of t. So is y. Is there any other way I can answer that question yes and be
Yeah,
accurate?
if it's sorry, go ahead.
No, I thought you were gonna answer.
Okay, and with respect to it's just with respect to like the the y-axis.
Yeah, so I also have x is a function of y, which is not usually something we look for. But in this case, that's absolutely true. Because, no matter what y value I pick, there's only one x value that can give that to me. But the thing we usually look for is I cannot say this. Y is not a function of x. Clearly, there are infinitely many places where you can give me a value of x and I have to give you multiple values of y. So any questions here, just kind of how to look at these things. This example is basically, how do parametric curves work? How can I plot them, and really, how can I understand them? Any questions about just this basic first look at it? Okay, so how about this one? So I got my parametric equations. They're both trigonometric. And I am not giving you an interval this time. But we have two trig functions. What's a good interval for t that makes sense based on what these underlying functions are? And to help you answer that question, I want to see the whole behavior. So what's a good interval for t so I can see the whole behavior of this curve?
A pi to minus pi.
Pi minus pi?
Minus pi to pi.
Okay. Yeah, that's a good one. Why'd you choose those?
Just the max value for cos and the bracket for cos inverse and the overlap between the brackets of cos inverse and sine inverse.
Okay. Oh, that's good. Another way to look at it, what's the period of these functions? How much does t have to change by for these functions to complete one cycle of what they're going to do? So hopefully you remember from looking at trig functions in the past, the period is going to be 2 pi. So a couple things here. The interval negative pi to pi would definitely work. I am going to, at least for this first one, substitute it for 0 to pi. But really, it would give us the same exact relationship, same exact behavior. For this one, let's just go ahead and keep everything non-negative. And let's go ahead and just take the quadrants. So t equals 0, pi over 2, pi, 3 pi over 2, 2 pi. All right, so what is x equal to? Or yeah, so go ahead and start giving me some values.
One and 0 for the 0.
Yep, 1 and 0, good.
And 0 and 1 for pi over 2.
0 and 1. I'll go ahead and fill in 2 pi since 0 and 2 pi are the same angle. Or they're coterminal, I should say. How about pi? What's cosine of pi?
-1.
-1. Sine of pi is 0. And then find it for 3 pi over 2, cosine is 0. And sine is -1. Totally copied this down wrong. All right. So now that we have those points, we can do the same thing again. Based on these points, what do we think is about to be graphed here?
It's a circle.
Circle. Specifically, what circle?
A unit circle.
It's the unit circle. So, yeah, unit circle, centered at the origin, radius 1. Don't expect this to look circular at all, but that's actually not terrible. But yeah, we're looking at a unit circle here. And this is a pretty common construction for circles in general, is to break them down parametrically into cosine t, into some cosine function and some sine function. And that's all because of this. Now, I have a graph of a circle that I can say is a function. So xy is a function of t, which is nice because usually when you deal with circles and you're trying, I mean, really all the calculus tools we have, like for derivatives, integrals, things like that, you're only allowed to deal with continuous functions. Continuous functions where either y is a function of x or x is a function of y. Just by all of the symmetry that a circle has, you have no hope of doing that. You can't represent a circle as a Cartesian function in any way. But if you get parameters involved, then you absolutely can.
Also, it makes sense. Like if you add the x square and y square, so it becomes sine square and cos square. That's 1.
Exactly, and that's not an accident. So x squared plus y squared equals. You've probably seen this relationship before, which that's a center of some radius r, centered at the origin. And if I if I substitute in my x and y based on that, cosine squared of t plus sine squared of t equals r squared. Clearly this. We've dealt with this in this class, and I'm sure when I showed it to you, that was not the first time you saw it. So we know that is the Pythagorean identity. That's equal to 1. So that means the radius of the circle is 1. So yeah, this one we're looking at the unit circle. Any questions there? All right, so how about this? I'm changing x and y. Basically, I've doubled both x and y. So what do we think that's going to do? What is this going to graph now?
Circle of radius 2.
Circle of radius 2? All right, let's find out. So this table is going to look a heck of a lot like the last one, except all these are going to be doubled. In this case, instead of graphing, basically, I'm going to have points on every axis, positive and negative, exactly 2 units away. And yeah, this is absolutely going to be a circle of radius 2. So circle of radius 2, centered at 0, 0. Any questions for that one? All right, how about this one? So now we are changing the argument inside the argument of the sine and cosine. So what do we think this is going to do? So we went from the unit circle centered at the origin to a circle centered at the origin, but twice the radius. What is that 2? Basically now I'm not doubling the amplitude, I'm doubling the coefficient on t inside the argument.
I don't know. Wouldn't it still be the same thing almost? Should
Same
be,
as
right?
what? Same as what? The last one or the unit circle?
The last one.
Okay, so let's see. Does it make sense to use the same interval 0 to 2 pi? So I'm going to make these subintervals a little different now. Instead of splitting this up into pi over 2, I'm going to split it up into pi over 4 and do those. So 3 pi over 4, pi over 4, 3 pi over 2, 7 pi over 4, 2 pi. So I'm just going to fill in the ones on the, we just did these. Actually, that's not true anymore. Can't do those again. So if we plug in t for both, or 0 for both those t's, that's going to be what we're used to. Just going to start at 2, 0 again. But now when I plug in pi over 4, I'm going to get 2 cosine of pi over 2 and 2 sine of pi over 2. That's going to give me 0 and 2. If I plug in pi over 2 to those, I'm going to get cosine of pi and sine of pi. So that's -2 and 0. Then 3 pi over 4 is going to give me an argument of 3 pi over 2. Be 0 and -2. And then pi, now I'm going to, that's 2 pi, -2 and 0. So based on that, then what should I do with these bottom 4 values? Do I need them?
No.
No. I mean these are trig functions, they're periodic, and I have already gone through one period. So I don't need these, which means I don't need this interval. What does my interval really need to be? Like how far can I cut it back from 0 to 2 pi? 0 to what?
0 to pi.
0 to pi. And that's all because if the period of a trig function of a sine or cosine function is 2 pi. And if I'm going to be doubling all my arguments, then that effectively cuts the period in half. But what is this graph going to look like?
Still circle of radius 2.
Circle of radius 2, right? So this XY graph is going to look identical to the one we just graphed. So in terms of X and Y, the graph is identical to the previous one, which looked like this: 2 cosine t and 2 sine t.
It's like you gave the graph a spin.
What do you mean by that?
I don't know. I just feel like that intuitively. Like you give it a spin.
Maybe I'm not totally sure what you mean by that, but I think, but based on something else I'll talk about later tonight, that might either solidify what you're saying, or you'll modify it a bit. But in terms of the graph, yeah, the XY behaviors are the same. So if you look at this graph only in terms of X and Y locations, coordinates of points, I haven't done anything different. something is different, but you kind of have to look deeper than the Cartesian plane to see it. And I think maybe that's all I'll say about this for right now. So we just showed basically how you can, I mean, really, if I go back, if I modify these numbers here, the coefficients of sine and cosine, you've probably seen that if I modify those, I can make a circle as big or small as I want. So I can definitely, I think hopefully right now, there are a couple of you who can see like how I can make a circle of whatever radius I feel like. But can we do even better than that? Can we generalize these so not only can I have any radius, but also can I move the center around? Every circle I've drawn so far has been centered at the origin. So is there anything I can do to move the center? So basically everything we've looked at today has had this form, x squared plus y squared equals r squared. This is going to be centered at 0, 0, radius r. Does anybody remember anything about what the equation looks like for a circle of any center? Can I generalize this equation so that basically I have some control over where the center is as well, not just the radius? All right, so
Is it x minus a the whole square plus y minus b the whole square equals r square?
yeah, it looks something like that. I'm just curious, did you remember that or did you have to look it up just now?
No, I knew it.
Okay. Yeah, and I'm sure everyone's seen this. I'm not sure most of you still remember it. It might have been a while. So still, this is going to have radius r. Where's the center?
A comma b.
Yep, center AB. And really, this comes from think back to when you learned about how to transform functions, or basically how to translate graphs left, right, up, down. That is the same principle that tells you basically why the center is at A and B. So let's go ahead and take a look at one of these. So I want to find a Cartesian equation for this parametric curve. So basically, basically what I want to do is get this into the form of, just x and y. I want to eliminate t somehow. And there's one thing we've kind of already talked about that will help us. So I know that a circle, basically I can generalize the circle x minus a squared plus y minus b squared is equal to the radius squared. So now I am giving you what x and y are. So let's go ahead and fill in from there. So 6. And x minus a. Oh no, that's why I wanted to put 6 there. 6 plus 5 cosine t minus a squared plus 7 plus 5 sine of t minus a all squared, or not a. These need to be different. Equals r squared. So if we go back a couple of slides, we know that if I if I square those brackets and add them together, I better get a constant. So what's on the left-hand side here needs to be a constant. So that might be too small of a hint, but let's try it anyway. If I know that, basically, if I were to expand these all out, that I should be able to simplify it down to a constant. We know, or do we have any idea? Maybe you're not right, but maybe you have a guess as to what A and B need to be equal to. Okay, so if we don't know, then
I'm sorry. It should just be 6 and 7.
why do you say that?
Yeah, because if you're gonna square it, it's just gonna be a 25.
Okay, so yeah, I mean, we can try that, and if it doesn't work, then we'll have to try something else. But basically, what we're hoping is this: if I square this bracket, so we're claiming that A is equal to 6, and that B is equal to 7. And hopefully that gives me a radius, or that gives me a constant. So clearly this is going to simplify down like this. And I'll get 25 cosine squared of t plus 25 sine squared of t equals r squared. If I do a little bit of manipulation, I can factor out 25 and get cosine squared t plus sine squared t equals r squared, and that's exactly what I wanted. This cosine squared t plus sine squared t is equal to 1, so I get 25 equals r squared. So r is equal to 5. And hopefully that makes sense with what we saw in the previous examples. Both of my cosine and sine have the same amplitude. So that means, yeah, hopefully you were seeing, even though you might not have been able to figure out right away or see where the center was going to be, hopefully you see that the radius is equal to 5. So from there, remember, we kind of started from this skeleton here. And I believe, based on what we got, that our initial claim for A and B were good. So I believe my Cartesian equation is like this: x minus a, which was 6 squared, plus y minus 7 squared equals 5 squared, which is 25. And trick question here. If I were to graph this, what shape would it give me?
Just put a 6 and a 7. That's would be a circle of radius 5 on 6 and 7.
Okay.
Centered it around 6 and 7.
So you're saying it would give me a circle?
Yeah.
Okay. I believe we're going to graph a shape centered at 6, 7. I do not believe it is going to be a circle. Why do I say that?
Yeah, that makes sense.
What should it be instead? Focus on this guy here.
Oh yeah, it's 25. Sorry.
So this interval right here, pi over 2 to 3 pi over 2, is that going to give me a full behavior of a circle?
A semi.
It's going to give me a semicircle. So let's see where the endpoints of that thing are. 6 plus 5 cosine pi over 2 and 7 plus 5 sine pi over 2. That's going to give me 5 cosine pi over 2 is 0, so that's 6. And 7 sine pi over 2, that's 12. So I have 1 point at 612. If I do the same thing with 3 pi over 2, then I'm going to get 6 again. So that gives me x equals 6 and y equals 7 minus 5, which is 2. So here's what I know. I have a semicircle with the center at 6, 7, and I have the 2 endpoints. So I know it's a vertical semicircle, but what part of it do I have? Do I have the right half or the left half? How can I figure out whether I have to graph the left half or the right half?
It's the right half.
How do we know?
Because if it's 0, it would be if you're oh yeah, it's hard.
Okay,
Yeah,
so
it should be the right half, right?
yeah,
Because
is there another t value we can try to be sure? So I plotted these 2 points. I'll go ahead and label which one comes from which one. This one right here comes from t equals pi over 2. This one here comes from t equals 3 pi over 2. What's another good t value to use that would give me, because I think if I can get a third point on this circle, or on this semicircle, I'll be done. So what's a good third value to use?
pi by 4.
Pi by 4?
No, sorry. Pi.
Pi is good, right? So yeah, right in the middle of pi over 2 and 3 pi over 2 is pi. So, didn't budget my space very well. 6 plus 5 cosine pi, that'll be 1. And then 7 plus 5 sine pi, that'll be 7. So if I graph it x equals 1, y equals 7, hopefully that's enough to tell you that I am looking at the left half of this semicircle. Last question about this thing before we move on. Which direction did I graph this? Did I graph it according to that arrow or that one? How is this graph traced? Which one of those two is correct?
From the top to the bottom.
From the top to the bottom, right? So yeah, remember we're graphing these things in t order. T equals pi over 2 is above, t equals 3 pi over 2 is below. So we're graphing it like this, or use a more precise term, we're graphing counterclockwise. Or if you prefer, anti-clockwise. Any questions on this one? All right, let's go for another one. This one, we can't rely on our trig identities for this one, but I want to find a Cartesian equation for this curve. So let's talk about, what a good attack for that would be. How would I do that? And when I say our Cartesian equation, what I really want to do is this. I have one of two goals. Either I get y, which is equal to a function of x, or I get x, which is equal to, I'll call it another function in y. So I have one of those two goals. And another way to say this is, no t. So basically the parameter will be absent from whatever I come up with. So does anybody have any ideas, any suggestions for how I can make that happen?
I'm sorry, Professor, can you repeat the question just one more time?
Yeah, so basically, is there anything I can do algebraically or using calculus to make one of these two situations happen? Really, I want an equation that doesn't have t in it anymore. So basically, you can kind of think of the parameter as this, this intermediate, middle
Logarithm?
variable, but I'd rather not use it. I'm sorry, what was that?
Logarithm?
Where would you apply it?
But so you have like x minus 1, like x plus 1, and then you take log, it would be.
Yeah. So let's manipulate this one. If I get x plus 1 equals e to the t. So Rias, you're suggesting a logarithm. Why a logarithm? What are you trying to do with it?
Oh yeah, because yeah, log, natural log to the of a raised to b is just b natural
Right,
log of
so
a.
it sounds like what you're trying to do is I want to solve for t. So that's basically what we started doing. Now what I want to do is this: natural log of x plus 1 is equal to the natural log of e to the t, which is equal to t times the natural log of e, which is equal to t. So I have t equals the natural log of x plus 1, which seems like a good move, but now what should I do with that?
Well, then you're gonna do the same thing for y and equate it, I guess. I don't know.
That would work. There's something we can do that's a little more direct. Because remember, all I want to do is get rid of t. And what if I just take what I found for t and just substitute this in?
That would work.
So I'm not going to let us finish here, but I'll just make a note. T has been eliminated. And this is the language you'll typically hear for this process. It's called eliminating the parameter. I have a function of x, I have x, which is a function of t. I have y, which is the function of t. I would really love to get to a place, and it's not always possible, but I would love to have x as a function of y or vice versa. Here's one more challenge, though. I believe I can write this equation here without an e in it. Any ideas how to make that happen?
It would just be ln x plus 1 the whole square.
Yep, so that's one property of logarithms is if I have a coefficient of a logarithm, I can just rewrite that as an exponent on the argument of the logarithm. So that's good. And then hopefully from there, you remember this is true. E to the natural log of x plus 1 squared just becomes this, y equals x plus 1 squared. And what kind of, if I were to have graphed this, what kind of curve would I have gotten? What is this the equation of?
Oh, 1, 0.
What do you mean 1, 0?
Whoa, sorry.
If I were to graph this, what would it be shaped
Oh,
like?
that's just a parabola
Yeah.
with the translation of 1.
Translation of 1, which direction?
To the bottom.
It's actually going to be to the left.
I'm sorry.
You're good. Yeah, so this is parabola with vertex at -1, 0. And how about orientation? Which way does this thing open up? Up, down, left, right?
Up.
Yeah, opens upward. So this is one of those cases where, we had a parametric relationship here, but it really wasn't worthwhile. It really made things more complicated. So, sometimes it's worthwhile to eliminate the parameter and see if you can. I mean, it's good to collect information. It's good to know things. So if you can eliminate the parameter and maybe that's easier to deal with, then yeah, definitely deal with that. Any questions for this one? How about this one? How can I find a Cartesian equation here?
Square and add.
Square, so square which one?
Works either way.
Okay,
And
so I
then
just want to make sure we're just going to stick with one. I think we manipulated X last time. Let's do Y this time. So really what I want to do here is solve for T. So that's, when you're trying to eliminate the parameter, this is probably the most direct way to make it happen. So I'll get y squared equals T minus 1. Or T equals y squared plus 1. And then I can put this into this T, and I get X equals the square root of y squared plus 1 plus 1. So I get X equals the square root of y squared plus 2. Can I do anything with that?
you can square it if you want.
We could square it. So let's go ahead and square it. See what we get. So then you're gonna have X squared equals y squared plus 2. Which maybe I'll do this. Does anyone remember what kind of shape this makes if you graph it? It sort of looks like the equation looks like a circle, but it's not going to be a circle. This is kind of optional. I kind of don't expect this one to come back from your memories. It's probably been a long time for this kind of thing. But this is the graph of a hyperbola. Which I'm going to guess you haven't dealt with the properties of hyperbola since pre-calculus, just because they don't show up often. But the biggest thing I wanted to look at, and really all of these are okay. I mean, I did not specify I want X to be a function of Y or Y to be a function of X. So really all of these, and there are certainly others that you could have come up with. Any questions here? All right, so new thing we haven't talked about, but I'm hoping you're not terribly thrown by what these mean. Basically, when you see the word initial, hopefully you have a certain preconception. Basically, when you see initial, think beginning, and terminal is the exact opposite. Think of the end. So my initial point if I want to find my initial point, what t value do you think I should work on?
Negative pi over 2.
Negative pi over 2, right? I want the least value of t in my interval. So when t equals negative pi over 2, I get these two things. X equals cosine squared of negative pi over 2. And y equals 4 sine of negative pi over 2. And what are these equal to? So cosine of negative pi over 2 should be 0. So squaring is going to be 0. And 4 sine of negative pi over 2, that should be 4 times negative 1, negative 4. So my initial point is 0, negative 4. But what about the, oh, should change the heading here. That is going to come from the greatest value in my interval. So that'll be t equals pi over 2. All right, so my initial point and my terminal point are respectively 0, negative 4, and 0, 4. So let's go ahead and graph what we know so far with the endpoints. All right, so I have initial was the lower and terminal above. Is there any way I can learn anything else about the anything else about how this graph is, or how this curve is graphed? Anything else I can look at?
Would we find the point at t equals 0?
Yeah, t equals 0. I mean, really, you could pick anything on the interval, like anything within the endpoints, but t equals 0 is perfect. It's the simplest one to think about. So if I get t equals 0, I'm going to have x equals cosine squared of 0, which is 1, and y equals 4 sine of 0, which is 0. So I know that I also have this point here. So is that final point enough to tell you, or to answer this question for us? Is this being graphed clockwise or counterclockwise?
Be counterclockwise?
Would be counterclockwise, and I'll just believe you just get this this curve here. Yeah, it is graphing from the bottom upward, and it's also starting out by going right and then left, so that is going to be counterclockwise. Any other questions here? Okay, keep on going. All right, so I want to sketch and identify this curve. So I'll go ahead and let you all drive. What can I do to help me answer this?
one of them is just always gonna be positive. The other one is always gonna be negative, right? Some negative terms.
I don't. So I agree that since I'm squaring this is always positive, but I don't think this one's always negative.
Oh, no. I mean, it has negative.
Oh, okay. Yeah. Yeah, one will be definitely positive or negative. So that's true. So I definitely know this is true. Y is greater than or equal to 0.
It's gonna be half of a. No, it shouldn't.
Does Y have a maximum that I can think about?
Yeah, 1.
Yeah, okay, good. So that's a good thing to know. Can I set up a similar interval with X? So X is equal to sine T. Do I know anything about the minimum, a minimum and a maximum there?
Would it be -1 and 1?
Goes, yeah, bounded below by -1 and above by a positive. So that's useful. I'm not going to start drawing it yet, but I basically know where my graph is going to be. What else can I do to help me understand what this curve is going to look like?
Actually, you can do something a little bit.
What can I do?
It's a little bit it's a small modification.
Okay.
You could rewrite sine T as 1 minus square root of 1 minus cos squared T, and then x squared, and then, oh, that wouldn't work, would it?
So I believe that's true. Sine of T is equal to the square root of 1 minus cosine T. What do you want to do with that though?
It wouldn't give us anything, right? Like, even if you rewrite it.
It depends on what you're trying to do with it.
as-
Can we eliminate the parameter?
Yeah, we can eliminate the parameter, that's for
Yeah.
sure.
How would we do that?
Yeah, you substitute that in for x and x squared, that you will get 1 minus cos squared, and then you add both of that.
Yeah.
Or you rearrange something and then add.
I think I know what you're getting at, but check this out. We know that x squared is equal to sine squared T, right?
Yeah.
So what else is x squared equal to?
1 minus cos squared T.
Anything else?
No, it's just,
Oh, it's
One
just, yeah.
yeah, but then you add both. No, you rearrange that. It becomes a cos. Man, it's not working.
So I think you're taking the long way around. What you're saying is true. I think you'll eventually get there, but I know that x squared is equal to sine squared T, but I also know that y is equal to sine squared T. So really the curve I'm graphing is this.
Oh my god.
Yeah, so I mean, yeah, I'm not sure. And it's one of those things that it's hiding in plain sight. Maybe it's not easy to see, but really this curve is no different from y equals x squared. But something to keep in mind here, if I were to graph this, I know what this parabola looks like. Draw the points in for me.
I don't know why I went all that.
Yeah, I'm sure that I'm positive you weren't not the only person who didn't see it. So I got this. I know this parabola looks like this. Would it be okay for me to draw this parabola like this, where it continues indefinitely in both directions? Is that okay?
No,
I hear no. How come?
because the equations for them like don't go over like the one.
Yeah. So remember, even though it eliminated the parameter, maybe doesn't make it obvious that there are sine functions involved in this parabola, and because of that, look at these intervals. X cannot be less than -1 or greater than 1, so I definitely can't stray to the left or right. And y never can be negative. We're covered on that, but it also can't be bigger than 1. So the fact that this curve is governed by sine of t means that, even after I've eliminated the parameter that I really need to, whether or not it's asked for, you should at least have this in mind. The domain is going to be, since I already wrote it in that notation, I'll write it in this notation this time. So yeah, I mean, I won't go through it, but I can promise you that eliminating the parameter will work here. Even the traditional way we did it, where you solve for t in one of them and then plug that into the other equation, that will certainly work. You can work through it, or I can go through it with you if you want to do it, but sometimes you can notice some other way to get to the end, and that's fine too. Anything else you want to talk about with this one? Okay. All right. So I've given you the Cartesian equation for a circle. And I've given you one of the functions for one of the parametric functions, x for t. I want to find, basically I want to find y of t. So how can I do that?
Would you plug in the x into that top equation?
Yeah, let's try that and see what happens. So here I get 4 plus 2 cosine t minus 4 squared plus y minus 5 squared equals 4. So that's a good place to start. So that gives me 4 cosine squared t plus y minus 5 squared equals 4. So I think that's a good first move. Where can we go from here? What are we trying to do? What's our end goal? So I'm trying to find y of t. So let's keep trying to isolate y. So from here, I'm going to go y minus 5 squared equals 4 minus 4 cosine squared t. Any ideas from there?
Y equals 5 plus sine squared t. No. Y plus
So
4 sine t.
let's break it down slowly. How'd you get there?
I'm so sorry.
Oh, you're okay.
I don't know. Like, I just know.
Okay.
I was thinking square root both sides.
Okay, square root both sides. So I get y minus 5 equals plus or minus this thing. 4 minus 4 cosine squared t. And let's go ahead and just solve for y then. So then we have this 5 plus or minus 4 minus 4 cosine squared t. But we have a problem. The way this is written right now is not a function, because for any value of t I plug in here, I'm going to get a plus or minus. So that means unless the thing under the square root gives me a 0, that value of t is going to give me, any one value of t will give me two y values, which is not how a function works. So basically, I have given you enough information to basically determine if it's positive or if I keep the plus sign or keep the minus sign. But before we try to figure that out, can I simplify this radical at all? What if I factor? Did that help? I'm gonna go ahead and do this. I can factor out a square root of 4, simplify it to 2, and now I have 2 times the square root of 1 minus cosine squared of t. Does this look familiar?
That's the square root of sine squared, right?
Yeah, so yeah, underneath this bracket, if you look at your, or think about your Pythagorean identities, what I have here is 2 times the square root of, square root of sine squared t. So I have y equals 5 plus or minus 2 sine t. But I need to choose one of those. So how do I choose that? So what does this graph look like? Probably easier to see if you look at the Cartesian equation. So I've kind of had a refresher on this. First of all, what shape is this going to graph, this equation?
A circle.
Is a circle. Now let's get the properties of the circle. Where's the center? Where's the radius?
The center is at 4 and 5.
Yep,
X
center is
equals
4, 5.
And the radius is 2.
Radius is 2. Yep. Radius is square root of 4. So let me plot those points in. Why? And I am also told that the circle is traced clockwise. So and really that clockwise property should help you figure out if I want 5 plus 2 sine t or 5 minus 2 sine t. So let's look at what the x is doing. 4 plus 2 cosine t. And I guess I should give you a terminal point here. What happens if t equals 0? When t equals 0, what point do I get on my circle? So x equals, oh, sorry, go ahead, Colin.
Yeah, I was about to say the x is 6.
X is 6. And then y, no matter what, no matter which one of those y's I end up going with, it's going to be 5. So my initial point is right there. So basically, I want t equals pi over 2. Basically, I know that I have a period of 2 pi, so let's just look at a quarter turn. Hopefully it's clear that looking at a half turn around the circle is not going to be helpful because I could have gone a half turn clockwise or a half turn counterclockwise. But I think doing a quarter turn will give me what I want here. So please let me know if I need to unpack that a little bit. I might have, maybe I'm making the leap that I should break down into smaller steps. Okay, so let's do this. T equals pi over 2. That means y is going to be equal to 5 plus or minus 2 sine of pi over 2. And this is where I get a branching path here. If I take the plus sign, that's going to be 7. If I take the minus sign, that's going to be 3. Which one do I want?
The 3.
I want the 3. So that means I have eliminated, basically I have now ruled out one of these. So I want y to be equal to 5 minus 2 sine t. Any questions with that? All right, let's go ahead and move on. Yeah, let's go ahead and do this one. So actually, we're gonna hold off on this one. So we're just about halfway through. I got 7:42. So let's go ahead and take a quick break. We'll come back at 7:53, and I'll see you all then. All right, let's go ahead and get started again. So our next section is basically taking curves that are defined using parametrics and performing calculus on them. So differentiation, integration, basically. So be a little bit quick because you've already seen these concepts before, but you've not seen them in the context of parametric equations. So let's go ahead and get started. So got a curve here given by these two parametric equations. And I want to find these three quantities. So dx dt, dy dt, and dy dx. So let's just handle them in order and think about it this way. You have seen this notation before. What does dx dt mean? So hopefully you recognize this as, this is Leibniz notation for a derivative. I want to find the derivative of x with respect to t. So this is just polynomial, so it's pretty simple. So this derivative will be 2t minus 2. Similar thing for dy dt. I want to find the derivative of y with respect to t. That'll just be 1. So how do we find dy dx? So it's our first time seeing it in the realm of parametric equations, so I'll go ahead and develop it for you. So think about what we have here. So far, the derivatives I have are dy dt and dx dt. So if I want to find dy dx, basically this is kind of an application of chain rule. I'm going to start with dy dt, but then I would really want to multiply that by this strange thing, which I don't really have. I mean, I do, but not in this form. So hopefully you can kind of imagine that if I take dy dt, multiply it by dx or dt dx, you know, if you're following the principle of chain rule, I will have dy dx. But really, we don't typically look at it this way. Typically, what you're going to look at is this: dy dt over dx dt, which we have. We have both of those intermediate derivatives. Now I can just take that ratio. This comes out to be 1 over 2t minus 2. So it might look a little strange, but this is your derivative of y with respect to x. And even though it's the derivative of y with respect to x is joining those two variables, the derivative is written entirely in t. So here are my three derivatives. Basically, to find dy dx, you need these two building blocks first, and then you can get this final derivative dy dx. So this is, I'll go ahead and call this out to the side here. This is something you're going to get a lot of use out of, because even though we have these parametric equations, remember we typically think of things in Cartesian terms. So y in terms of x. So it would stand to reason that we want that derivative. I want to know how the rate of change of y with respect to x. Oh, did the wrong way. dy dt over dx dt. Any questions there? All right, let's go ahead and move on. So, got a few things to do with this one here. So I have a curve defined by these two parametric equations. Basically, I'm going to take all these different steps here and I'm going to use that to sketch a drawing of this curve. So I want to show that this curve has two different tangent lines at this point 3, 0, and I want to find their equations. So what's happening with this curve? If I were to graph this, how could this curve have two different tangent lines at the same point? What's happening there?
The graph is like overlapping at that point.
Right, it overlaps. So basically, the graph intersects itself. So basically, we know this is going to be true. I know that. Let's just set these things equal to that point. So t squared equals 3, and y equals t cubed minus 3t, which is equal to 0. Top equation pretty clearly gives me this: t equals plus or minus radical 3. So that tells me that, okay, I believe there are two t values that give this. But this, if I factor to t, I'll get t times t squared minus 3 equals 0. So this tells me that there are three different places, or the three different t values that give me a y coordinate of 0. And that's going to be t equals 0 and plus or minus radical 3. Clearly, if you plug in 0 back to the x equation, you're not going to get 3. So I can throw this one out, and really my two t values are plus and minus radical 3. So there, I've already shown that I'm going to have basically two different t values that give me the 0.30. So now to show that there are two distinct tangent lines there, I should probably find the derivative. So remember, when you're trying to find the slope of a tangent line or the equation of a tangent line, you need to know something about the first derivative. So let's go ahead and deal with that. I know that, and let's just go through it the way we did it before. I need to find dy dt, which is equal to 3t squared minus 3, and dx dt, which is equal to 2t, which means dy dx is equal to that quotient, 3t squared minus 3 over 2t. Any questions on how I've gotten this derivative? I don't want to simplify it. Yeah, let's do this. So it's going to have to be 3 halves times t minus 1 over t. Okay, so now what can we do with this? So actually, that simplifying is probably going to make things more difficult than it needs to be. So let's just work on one of these tangent lines. So I have two different cases here. Let's work on the case where t was equal to negative radical 3. And I want to find the equation of the tangent line that happens in that point. So how do I start working on this? This is something I'm sure you've done a lot of, and really it does not work any differently with parametric. So if I want to find the equation of a tangent line, what do I need to do? All right, so in order for me to find the equation of the tangent line, I first need to evaluate my dy dx there. So dy dx would be equal to 3 times negative radical 3 squared minus 3 over 2 times negative radical 3. Simplify, I get 3 times 3 minus 3 is going to be 6 over negative 2 radical 3, which comes out to be negative 3 over radical 3, which is negative radical 3. So that's my slope. And now what I really want to do is, I'm looking for the equation of a straight line. So I know basically I'm trying to, let's just look at slope intercept form. Y equals mx plus b. I have found my slope. That's what the derivative gives you. It gives you the instantaneous rate of change, basically the slope at that point. So I know that I can use negative radical 3 as my slope. So negative radical 3. Do I know my coordinate for x? I do, because the whole point of this was that I'm looking at 3, 0. So negative radical 3 times 3 plus b, and my y value was 0. So that means b is equal to positive radical 3 over 3. So then the equation for this tangent is this: y equals negative radical 3 x plus 3 radical 3. All right, so let me know if you have any questions, but I'm just going to get that other tangent line now. When t is equal to radical 3, I'm going to have basically a very similar calculation, just substituting a different value. So again, numerator is 6, denominator is this time positive 2 over radical 3. This comes out to positive radical 3. And this time I'm going to get a similar looking tangent line, but my slope this time is radical 3. X is still 3 plus b equals 0. So this time I have y equals radical 3x minus 3 radical 3. Any questions about where I got or how I got those tangent line equations? All right, so next thing I want to look at is I want to find the points on this curve where the tangents are horizontal or vertical. So let's just deal with horizontal first. So here's what I know. Basically, and I'll draw a small graph here, maybe up here. And I'll draw, doesn't need to be that complicated. So I'm looking at a couple of different ideas. This point right here, if I were to draw a tangent line to it, that's going to be horizontal. And then right here, this is going to have a vertical tangent line. So at this top point where I have a horizontal tangent line, is there anything I can say about the values of certain derivatives at this horizontal point? And remember, I took 3 different derivatives here. So is there anything I can say about dy dt, dx dt, or dy dx at that point where I have a horizontal tangent? Can someone confirm that you can hear me?
Yeah. Could you repeat that question?
Yeah. Yeah. So for the I'm looking for this horizontal tangent line. Is there anything I know about the derivative for that point or any point where the tangent line would be horizontal? So really what's going on here is, you know, think about this in terms of rate of change. If I have a horizontal tangent, y at this instant, y is not changing. So because of that, I can say this. I can say dy dt is equal to 0. Because at that instant, at that point, that value of t, y is not changing. It has 0 change. But similarly, what can you say about this? If I have a vertical tangent line, what can you say about what similar thing can you say about another rate of change? I don't know if you can see that, you know, if I have a vertical there, then that curve is not moving, it is not changing in the x direction. So in that case, I have dx dt equals 0. So we can use that idea to figure out where basically where my curve is horizontal and where it's vertical. So horizontal, like I said, I'm looking for dy dt equals 0. So dy dt equals 0 equals 3t squared minus 3 equals 0. And that gives me t equals plus or minus 1. But here's the thing. No, maybe I'll split these up a little bit. So one important thing for the horizontal point is that dy dt is equal to 0. But even though my function is not changing in the y direction, it certainly is changing in the x direction. So let me fill these two pieces of information in, and then I can talk about why that's important. So for a horizontal tangent, I need dy dt to be equal to 0, and I need dx dt to be equal to anything else. It just needs to be non-zero. Vice versa for a vertical tangent. And the reason for that is this. Think about this. If you have dy dt equals 0 and dx dt equals 0, then that means you have dy dx is undefined. And because of that, basically that means that your derivatives can't exist. You have no derivative there. Your derivative can't exist. So in order for the horizontal and vertical nature to be there, you really need to have one of these derivatives be equal 0 and the other one non-zero. So really we should take both of these first. So dx dt is going to be equal to 2t equals 0, and that gives me t equals 0. So hopefully it's clear from that that I'm not going to have that situation where I have dy dx being undefined. Or sorry, dy dx will be undefined if dx dt is equal to 0, but basically what you're not going to have here is that these t values aren't shared. So that means I know that I'm going to have a horizontal tangent at these two t values. I know I'm going to have a vertical tangent at that single x or that single t value. So let's go ahead and keep going. When t equals -1, that gives me this coordinate, x equals -1 squared, and y equals -1 cubed minus 3 times -1, which is 1 and -1 plus 3, which is 2. And let's also do t equals 1. And that gives me another point of, I'll accelerate this one a bit. 1 and -1 minus 3, -2. Any questions about how I developed, how I found these 2 points where the tangent was vertical? All right, so let's do the same thing for vertical. When t equals 0, I get the point x equals 0 squared and y equals 0 cubed minus 3 times 0. So I get the point 0, 0. So vertical at 0, 0. So any questions about this slide before I move on to answer the rest of this question? Okay. So we handled the first 2. All right, so got these first 2 on the last slide. Now, third question here. I want to know where the curve is concave up or down. So, you've done this before, probably. I'm sure you did this in Calc 1 plenty of times, but how do I figure out concavity? What is that? What do I need to do to be able to answer this question of where it's concave up or concave down?
You take the
Rios, I didn't catch the end of that. Take the what?
I'm sorry, I forgot.
Okay. Anyone else remember? How about inflection points? Does that concept ring a bell?
I mean, you could do one thing that I remember. It's like how that the derivative changes. Like if it's negative, that means like it's increasing, and then sorry,
Right.
it's
So
decreasing, and the
that
positive
comes, yeah, that comes from the first derivative. But the first derivative cannot tell you about concavity.
no, the second derivative.
Oh, I didn't hear you say second. Okay, so basically for concavity, we need the second derivative, which I'll write like this. D squared y dx squared. So what do we have so far? We have, basically we need to build that up from dy dx. So how do we do that? So I'm trying to find d squared y dx squared, which, if we weren't dealing with parametrics, we could just do this. I'm going to take the first derivative with respect to x of the first derivative of y with respect to x. And this is, whether or not you realize it, when you're taking a second derivative, typically with Cartesian functions, I'm just taking the first derivative and taking the derivative of that. So yeah, I'm taking, with respect to x, I'm taking d dx of dyx. But remember, now we're dealing with these parametric functions, so I really need to think about this like this: d dx of this thing, dy dt, all over dx dt. But another thing to consider, since we're also dealing with this in parametric functions, remember, if we go back, my derivative for dy dx, and maybe I should write it here. Dy dx is actually a function of t, which makes it impossible for me to find dx dt.
But you convert everything in terms of x, right?
No, I'm actually not going to do that. I'm going to devise a way to keep everything in terms of t, and basically I'm going to use the chain rule for that. So instead of taking this derivative with respect to x, I want to take this derivative with respect to t. So here's what I'm going to do. I'm going to multiply this by, and it might seem a little strange, but this is essentially what I'm doing. I'm going to bring in this new thing, dx dt, which I have. I have dx dt. So I want dx dt times everything else that I've placed in here prior, times ddx. Didn't make that big enough. But I brought in this dx dt, and the only way I can do that is if I, if I balance this. So I'm going to multiply it by dt dx, which is, so essentially what I've done is I have multiplied my previous step by 1 in this strange way, because basically dx dt times dt dx, assuming those are both defined, assuming they're both non-zero, that just comes out to be 1. So what happens when I bring these extra pieces in? Basically, dx dt times ddx of all this other stuff here, this comes out to be exactly what I wanted. ddt of dy dt over dx dt. And the reason I wanted that is because if you look at my derivative dy dx, I can't take a derivative of that with respect to x. There's no x's left. So I really need to take a derivative with respect to t. And then multiplying by dt dx it'd be easier for me to think about this like this. Instead of multiplying by dt dx, oh, everything went away. I want to divide this whole thing by dx dt. So this right here, spent a long time developing it, but this is also something we're going to need to use heavily. Now there are, just like in Cartesian, when you're in Cartesian, Cartesian situation, the second derivative is hugely useful for certain things that the first derivative can't tell you. For example, first derivative is good for telling you where a function increases and decreases. It won't tell you anything about where a function is concave up or down. So now that we have this, this is all building up to, I need to know where this curve is concave up or down. So I'm going to use this method here to find my second derivative. So let's just do it in pieces. I want to take the derivative of dy dx, and that's going to, with respect to t, so that will be equal to 3/2, not 32. 3/2 times 1 plus 1 over t squared. And then dx dt, I'll just not bring that over from the last slide. What was it? Dx dt is just equal to 2t. Therefore, I get d squared y over dx squared. That's equal to 3/2 times 1 plus 1 over t squared all over 2t. And would really love to simplify this. So 3 minus 3 over t squared over 4t. Multiply every term by t squared gives me 3t squared minus 3 over 4t cubed. And I think that's probably the friendliest I'm going to make that second derivative look. Any questions there? So a while ago, I asked about inflection points. Does anyone remember what those are and how to find them?
You take dy by dx. You could equate that to
Sorry, Reese, I think you're cutting out a little bit, but yeah, basically, the deflection points happen when the second derivative is equal to 0. And really, to find the derivative, I want to know if this derivative is equal to 0. So that's really going to come from what makes the numerator equal to 0. So I'll take a look at that. So I get 3t squared minus 3 is equal to 0. And then that comes out to be t giving me plus or minus 1. But I also need to look at where the second derivative is not well defined. So if I look for where this function, this second derivative is not defined, what would cause the second derivative to be undefined? What was that?
T equals 0.
How'd you get that?
Oh, I mean, sorry, what was the question?
Yeah, so you're right. That's t equals 0 is going to make this undefined. But how'd you figure that out? So basically where that's going to come from is, I have a rational function for my second derivative. So it's only going to be undefined when the denominator is equal to 0. So that is indeed where t equals 0. So if I want to analyze concavity, sort of running out of room, so let me redo this and write it above. D squared y over dx squared equals, or is undefined, implies that 4t cubed is equal to 0, which implies that t is equal to 0. So really what I want to do is this. I'm going to make this spectrum for t. And I know that I have an inflection point at t equals -1. I have an inflection point at t equals 1. And I have, basically my second derivative is not defined at t equals 0. And I'm going to go ahead and fast forward here a little bit to get some time back. But really, you can find that concavity like this. I know that d squared y dx squared is equal to 0 here. I know that d squared y over dx squared is undefined here. And I know that d squared y over dx squared is equal to 0 here. So basically, I'm gonna have to check a few different intervals. I need to know what happens when t is less than -1. I need to know what the concavity is when t is between -1 and 0. I need to know what happens when t is between 0 and 1. And I need to know what happens when t is greater than 1. So why don't we just do one of these intervals, and we'll hopefully that'll give a good template for how to find the concavity of the other ones. So let's say I want to find the concavity when t is greater than 1. Any thoughts how I can do that? So the good thing about finding finding inflection points is that not only do I find all the places where the second derivative is equal to 0, but the more important thing, but probably more subtle thing, is I have found that there can be inflection points nowhere else. So if I choose a test point here, let's say t equals 2. If I find the concavity at t equals 2, then I have really found the concavity everywhere where t is greater than 1. So let's just find that one. When t is equal to 2, I get d squared y dx squared is equal to 3 times 2 squared minus 3 over 4 times 2 cubed, which is equal to 3 times 4, 12 minus 9, or 9 over 32. And I care less about that specific value than I do about the fact that it's positive. And that positive tells me that from here, from t greater than 1, I have concave up. Any questions on how I did that or how you would go through the rest? So as an exercise, I'll leave here. Find concavity. On remaining intervals. All right, let's go ahead and move on. All right, so I want to find tangent to this function called a cycloid. And basically, I'll go ahead and draw a sketch of it. Basically, what a cycloid is imagine you have a circle that has, let me draw it first and I'll be able to explain where it came from. You kind of have this periodic function. And basically the idea behind what generates this is you have a circle rolling around on the ground, and basically that function is generated by if you just pick a point on that circle and you're measuring its height. Basically you're measuring its horizontal and vertical position at all times. So it makes like this these half curves. I don't want to call them circles or parabolas because that's not what they are, but yeah, it makes those arcs there. So I want to find the tangent to the cycloid at this point. So that's the first thing I want to do. How do I get that done? How do I find a tangent line or find the equation of a tangent line? All right, so we need a tangent line. So I really need to find dy dx. So I need to build that up slowly. I don't think there's a good way to eliminate the parameter here. So let's find dy d theta. that'll be equal to r times sine theta. And let's find dx d theta, which will be equal to r times 1 minus cosine theta, which means dy dx, or yeah, dy dx is equal to r sine theta over r times 1 minus cosine theta, or sine theta over 1 minus cosine theta. So I am looking for a specific theta value. So now I can let, oh, not t this time, theta equals pi over 3, gives me dy dx is equal to sine of pi over 3 and 1 minus cosine pi over 3, which is radical 3 over 2, over 1 minus 1/2, which is 1/2, or finally radical 3. So from there, again, you want a tangent line, so you're looking for a equation of a straight line. And I found the slope. So radical 3x plus b is equal to y. And really, I need to find out what x and y are. So x is equal to r times pi over 3 minus sine of pi over 3. So that'll be equal to r times pi over 3 times, or yes, minus radical 3 over 2. And y will be equal to r times 1 minus cosine pi over 3. So that's 1/2 r. So now from here I get r over 2 equals radical 3 times r times pi over 3 minus radical 3 over 2 plus b. Let's see if this simplifies nicely at all, or if I can just so this is going to be really nasty looking, but I'm just going to go ahead and fill everything in. I know that m was equal to radical 3 x plus b, which is going to be hideous, but that's fine. Plus r times 1/2 minus 3/2. I guess just say minus r. Change my mind again. So that gross thing is our equation of our tangent line in Cartesian form at that point where I was interested. All right, so now I want to find the points where the tangent is horizontal or vertical. So what do I need to do to figure that out? All right, so I want to find out where these things are equal to 0. And I'm only gonna look at one interval. So let's say theta is on the interval from 0 to 2 pi, because I know this will repeat. So the only way that sine of theta is equal to 0 is either at 0 or 2 pi. What about dx d theta? R times 1 minus cosine theta is equal to 0, which means the only way that's going to happen is if cosine of theta is equal to 1. And the only times that happens is 0, right? I think it's also 2 pi. Oh, no, I messed up here. For the sine one, it's 0 pi or 2 pi. So now here's what I have. I know that it's 0 and 2 pi. I'll write this out specifically. At theta equals 0 or 2 pi, dy dx is undefined. And let's look at this graph of the cycloid above here. Really 0 and 2 pi are happening here. Theta equals 0, theta equals 2 pi. And imagine trying to draw a tangent line, for example, at those points. At these points on this curve, the derivative doesn't exist. And that's because dy d theta is 0 and dx d theta is 0. So the derivative just doesn't exist. Can't be computed. So that means I can throw out 0 and 2 pi. So really, there are no points where dx d theta is equal to 0, where dy d theta is not equal to 0. So there are no vertical tangents. So no vertical tangents. But I am going to get a horizontal tangent when t equals pi. And the way we find out where that horizontal tangent is just plugging in pi to the equation. So r times pi minus sine pi. That just gives me r pi. And y equals r times 1 minus cosine pi, which is equal to 1 minus -1, so 2r. So pi r and 2r. Which, if you look at our graph, that's going to have to be pi r 2r. Any questions there? Okay. All right, so now that was differentiation. Now let's look at area. So before we get into area, let's look at let me put this graph back on here. And really, I just want to find the area under one arch here. So I am not giving an interval, but I should find out what my interval is if I want to find the area underneath this one arch. So any ideas on how I can find that? Basically, I want to find a theta interval that I can use to investigate this area. All right, so basically where an arch begins and ends is all going to be given by, you know, I begin at y equals 0 and I end at y equals 0. So let's figure out where y equals 0. So from there, I'm going to get 1 minus cosine theta is equal to 0, or cosine theta is equal to 1, which happens at the first two places. The first two theta values that's going to happen are 0 and 2 pi. Really, it's going to happen every even multiple of pi, but I only want one arch, so I only need this interval here. So from here, I know that I am looking at an integral from 0 to 2 pi. But what am I going to integrate? So I know, let's just take one representative rectangle here. Okay, so what's the height of this rectangle? What is mathematically going to represent the height of this rectangle?
The y function.
It's gonna be the y, right? So for now, let's just call this y. What gives me the width of this rectangle? Remember, I want it to be as narrow as possible.
Just dx.
It's just dx. So really what I'm integrating here is, and maybe I'll make this more general first. I'll call this theta min. From theta min to theta max, y dx. Really, we've already figured out what the interval is from 0 to 2 pi. But remember, I'm only allowed to integrate with respect to one variable. What variable is that going to be? And really, I'm going to have to do this whole thing with respect to the parameter. And really, the fact that we're going to be integrating from 0 to 2 pi, hopefully that makes it clear. I mean, those limits of integration always have to be values of the variable that you're actually integrating with respect to. So I'm integrating from 0 to 2 pi, y, which is r times 1 minus cosine theta, and then dx. What is dx? So again, I'm going to bring in chain rule because really I don't want to integrate with respect to x. I want to integrate with respect to theta. So I'm going to rewrite dx as dx d theta times d theta. And hopefully that's clear from chain rule, and hopefully it looks similar to some of the other manipulations we've done tonight. Or now, really what I want to do is now I can take a derivative of dx d theta, so it'll be r times 1 minus cosine theta times dx d theta, which is going to be r times 1 minus cosine theta d theta. Clearly I can square this. And I don't need to have r squared inside the integral. So any questions about how I've gotten here so far? Okay, so I'll go ahead and expand this out. R squared times the or integral from 0 to 2 pi of 1 minus 2 cosine theta plus cosine squared of theta, d theta. So now we're going to have to rely on something we've done earlier this summer. You could easily integrate 1. You could easily integrate negative 2 cosine theta. We can't easily integrate cosine squared theta. So in the past, how have we dealt with this? I think I have definitely asked you this on quizzes and homeworks. I might have even put this on a test. How do I get the integral of cosine squared theta? What do I have to do to it? So one thing I'll remind you here of is double angle identities. So I can use this to get to a place where I can substitute in for cosine squared theta. I need to get another version of this, which I can get from a Pythagorean identity. So I would really like not to deal with sine squared theta. So I know that sine squared theta is equal to 1 minus cosine squared. So that means I can simplify this to 2 cosine squared theta minus 1. And from there, I can get this. Cosine squared theta equals 1/2 plus 1/2 cosine 2 theta. So now I can use that to now make this derivative something I can deal with. So I got 1 minus 2 cosine theta plus 1/2 plus 1/2 cosine 2 theta. Okay, so now I have three terms that I can deal with directly. So now we can go ahead and take the antiderivative. So r squared times 3/2 theta plus 1/2 cosine 2 theta. Antiderivative of cosine is sine. And then a chain rule says I have to divide by 2. So that's plus 1/4 sine 2 theta minus 2 sine theta, evaluated from 0 to 2 pi. So I get r squared times 3/2 times 2 pi plus 1/4 times sine of 4 pi minus 2 sine 2 pi minus all these things evaluated at 0. So 3/2 times 0 is clearly 0 minus 1/4 sine of 0. And then plus 2 sine of 0. So a lot of these things go to 0, which is nice. 3/2 times 2 pi is just 3 pi. This is 0. This is 0. This is 0, and this is 0. So really everything went to 0 except for one term. And I get a final result of 3 pi r squared. So like I said, Go ahead,
Professor?
Rios.
Um, can I don't know. Is that an area?
Is that a what?
Is that an area or something like this 3 pi r square?
Yeah, that's what we're finding, right?
Oh,
So yeah, think about the way we set this up. I mean, I drew this representative strip here. So this is a rectangle. Height of the rectangle is y. And width of the rectangle is our differential dx. So yeah, think about where we started here. This is kind of our usual way to find an area under a curve by integration. Yeah, basically what so think about how I described the cycloid and how you build it, or like kind of where it comes from. Basically, you have a circle rolling around, and if you imagine a dot on one point of the circumference of that circle, basically the cycloid is being traced out by that dot. And really, the area under one arch of the cycloid is 3 times the area of the circle that's doing it. And that's really what was shown here. Any questions for me at the moment? Okay, so I had a little more to get through, but getting the sense that a lot of you maxed out a while ago. So if that describes you, like I said, I did this calculus in 6 weeks when really it's a 16-week course. I know that's tough. I know it's exhausting. So if you did kind of get burned out today, and I'm pretty sure some of you did, take a breather, take a rest, but it still is important that you kind of get the hang of this and understand what we're doing. So please go back and revisit the video. Not tonight, maybe not even tomorrow, but at some point. Yeah, we like I said, there's a lot of class left, even though we got 5 weeks behind us now, only 1 week to go. But really, there's a lot left that can change. And I'll just, even though I've definitely said it more than once, I'll go ahead and say it again. If you need anything, please reach out to me and I'll work with you. If there are no questions, I will say good night and have a good weekend, and I'll see you all on Tuesday.
Thank you, Professor.
Thank you.
Professor, this is interesting.
Good.
You could just the math is almost fun for me because I'm a math major. But the thing is, you saw this emoji stuff?
I saw what?
Like you could I mean, you have a corner of the Zoom stuff, like you can put in emojis and stuff like that.
Oh yeah.
Yeah, that's, I don't know, I never knew that. Anyways, Professor, can you explain that one? I don't know. Sometimes I feel like something's happened. Like the graph, the remember the one that we talked about, the same thing again, the circle with the radius of 2.
Oh.
Yeah, that one. And it and you change the parameter by, like, you multiplied it by 2 or something. And
Yeah,
something
so
changed.
basically from this one to this one.
Yeah, exactly.
Okay, so basically what's happening there is, if I were just to show you both graphs, there's no difference. You wouldn't be able to detect the difference. Oh yeah, I forgot I was going to come back to this. So basically what's happening is, let me actually go back in here and
No, is my intuition right? Like, are you just like, it's like spinning a top?
yeah, and basically, so let's go with that spinning the top analogy. What's the difference in the way these tops are spinning from example 3 to example 4?
Oh, there's just like opposite or something.
Not really
Wait.
opposite. So let's look at this now. Now that we have the calculus tools, let's find dy dx. So dy dt over dx dt is going to be 2 cosine t over -2 sine t, and that gives me negative tangent t. So hold that thought. So this one basically, yeah, the rate of change of y with respect to x has everything to do with tangent t.
Okay.
But if I look at this one, dy dx is equal to 4 cosine. No, not 4 cosine.
-4.
Yeah, I don't know why that stopped me. Okay, -4 sine 2t. And this other one's going to be 4 cosine 2t. And this didn't make it really obvious, but we can maybe look at it anyway. Not -4. This will be negative tangent 2t. But let's just pick a value of t now. So basically I don't want to do t equals 0 because that's not going to do anything for me. But if I do, what's the value I can use? It's not going to be 0 or undefined. Just do 1. So negative tangent of 1
Oh, it's just the interval changes. That's all.
just the what?
It's just the interval that changes, right?
Oh yeah, the interval changes, but that's not all. So really, think about it this way. And you know what? This is going to be a lot better way to explain it than whatever I was trying to do just now. So this circle, it takes 2 pi radians to trace that entire circle. But this one, it only takes pi radians to trace the entire circle. So basically, I'm using the word time here, but there's really nothing here involving time. I just think it's an easy analogy. Basically, I'm traveling twice the distance in the same time. So the only real difference between these two examples here, or not
Oh, so the top is spinning faster.
Yes, one of them. Yeah, this top is spinning twice as fast as this one, but they both spin in a circle, and they're both the same. They're both the same size top, and they both spin the same way. But you can look at it 2 ways. One of them is going to cover more distance in the same time, or they're going to cover the same distance, but one's going to take half the time as the other. But that quote unquote speed is not visible if all I show you is the graph.
No, but so I feel like I want to say it's faster, but I don't know how to say it's faster.
Yeah, so yeah, that's, and I kind of screwed up too, because I said I used time when really time is not what we're doing here. But what you can say is that rate of circular rotation is twice as great for this one as it is for this one.
That makes sense. Yeah, and for the that was at the finals. It's gonna be on Thursday, right, Professor?
Yeah, it's next Thursday.
Oh, okay. And no, yeah, that's it. Professor,
Okay.
if you don't mind, can I ask you for a small help? Like,
Yeah,
I was
for sure.
for the I was there in the AC the Putnam team for this December, but then I don't know how to prepare for it because I just don't know what that is, or
I'm sorry, to prepare for what?
it's a thing called Putnam. The
Okay,
Putnam exam.
Yeah, I don't know.
Yeah.
I don't know much about that.
Yeah, like it's an exam, but yeah, it's okay if you don't know. It's all right.
Let me look into it. So, and I don't know if you probably have figured this out, but I did my undergrad math a long time ago, and I didn't do it at ASU. So yeah, I have not done a lot of the same things that you all have.
Yeah,
Just
but it's
different
just
school,
that
different time.
yeah, it's just that I do not know what that is or how to